Welcome you all to session 4 of the chapter Linear Momentum. This session will be exclusively on elastic collision. We have already studied about elastic collision. So what is elastic collision? It is a collision in which both momentum as well as kinetic energy are conserved, and the forces involved in elastic collision are conservative in nature, and there is no loss of kinetic energy in case of elastic collision. Now we will be discussing about elastic collision in two different frames. Okay, we will be discussing first with the laboratory frame of reference, then with center of mass frame of reference. Okay, let me begin with the first one, that is laboratory frame of reference. Okay, laboratory frame of reference. Okay, this is the first one, right? We are discussing about elastic collision between two particles, means collision between two particles which do not stick together, right? There will be collision of two particles, but this time they do not stick together and they move in different directions, right? I am taking a particular case of two-dimensional collision, right? So we will be discussing the elastic collision in two dimensions, means after collision the particles move in a plane in different directions. Let me take that case and discuss now here, right? Okay, now let me begin with the first, that is laboratory frame of reference, right? For example, first let me take a particle mass m1, particle of mass m1, and this particle is moving with velocity, let me take it as u1, right? And let me take the second particle, that is of mass m2, which is at rest, right? Okay, now this is the case before collision. After collision, these two, for example, let me take now here, after collision these two move in different directions in a plane. Okay, after collision, see here, the case is like this. There is a particle m1, there is a particle m2, this is moving, right? This is at rest. So when these particles collide, right, see here, this is before collision. When they collide, they move in different directions like this, means they are moving in different directions but in a plane, right? That is why I told you I will be discussing about elastic collision in two dimensions. Okay, let me take a mass m1. So this is a particle, let me consider like this. This is a particle and the velocity of this particle is in this direction. Let me call that as v1 here, right? Okay, let me consider here this particle. What is this particle? m2. This is, let me call it as m1. This particle is m2, and this particle moves with the velocity in this direction. What is this direct? What is that now here? v2, right? Okay, now this particle, right, moves in the direction of v1, right, making an angle. What is that angle it makes now here? Let me call it as theta 1, and let me take this angle is theta 2. Let me tell that m1 makes angle theta 1 along x-axis, m2 makes angle theta 2 along x-axis. Let me call this as x-axis, right? Since it is two dimensions, I will be considering both the axes. One is x-axis and another one is y-axis. Let me consider this is a y-axis now here, right? Now let me write about this, what actually it is. Let me begin the derivation here, right? Okay, consider two particles of masses m1, right? This is the first particle's mass m1 moving with velocity u1, right? m1 moving with velocity u1 and m2, what we say now here, at rest. Okay, let me consider two particles of masses m1 and m2, m1 moving with velocity u1 and m2 at rest. What happens after collision? Let us check it. Okay, this is the thing before collision here, right? This is after collision. After collision, let me write like this, right? Consider two particles of masses m1 moving with velocity u1 and m2 at rest, right? Okay, after collision, let me take what happens after collision here. After collision, m1 moves with velocity v1, m1 moves with what we say here, velocity v1. m1 moves with velocity v1, making angle theta 1. Making what we say here, angle. What is that angle? Theta 1. And m2 moves with, okay, what happened to m2? m2 moves with velocity. With which velocity m2 is moving? That is v2, making angle. What is the angle it makes now here? Theta 2. Right? So theta 2 with which axis now here? X axis. So let me take these two are angle with the x axis. Right? Let me write like with x axis. This just is an introduction of what I have drawn here. Right? So after collision, these two move with different velocities, making angle theta 1 and theta 2 with what we say now here? X axis. Right? Okay. Now, let me go with the mathematical equations for this elastic collision and calculate what are the final velocities of the particles after collision. Okay, let me begin now. Now, first of all, do remember, during any type of collision, momentum is conserved, right? So do remember, momentum is conserved in all type of collisions, but in elastic collision, kinetic energy is also conserved. Taking that concept into consideration, let me begin with mathematical equations now here, right? First of all, what is conserved in this collision? Momentum. Let me write. Momentum is conserved, right? In all type of collisions, momentum is conserved, right? So as momentum is conserved, but this is two dimensions now here, means we need to take two equations there, right? So along x-axis and along y-axis, right? Here, as the particles are moving in the plane, right? Plane is a two-dimensional. We need to speak about two axes now here, right? First of all, let me speak along what we say here, x-axis, right? First of all, let me speak about along x-axis. Let me write conservation of momentum, and afterwards I will be writing conservation of momentum along y-axis, right? Means total momentum before collision is equal to total momentum after collision, but we are considering along two different axes. First, let me write along x-axis, right? Along x-axis, is this particle moving along axis? Yes. What is the momentum now here? Momentum is m1 u1. It is not having any momentum because it is not moving at all, right? So what is total momentum before collision along x-axis? m1 u1. Let me write like this, m1 u1, that is equal to, what is the momentum of the particle m1 along x-axis? So what is its momentum? Let me write now, right? So first m1, what is the velocity along x-axis? Velocity along x-axis, how to write? We know the component of v1 along x-axis, this is angle is what now here? Theta 1. What is the component of v along x-axis? This side is adjacent side for theta 1. If it is adjacent side, what is the component of velocity? v1 cos theta 1, right? Okay, now m1 v1, what we say here? Cos theta 1. Let me write like this. Okay, what is the component of velocity v2 along x-axis? Right, this is which angle here? Theta 2. So this is adjacent side, again it will become v2, which now here cos of theta 2, right? Both are in the same direction, right? So I can take it as positive there, right? So m1 v1 cos theta 1 plus along x-axis, I am speaking only about along x-axis, m2, what is the velocity along x-axis? That is v2, what we say here? Cos of theta 2. Let me consider this as equation number 1, right? I got equation 1 by using conservation of momentum along x-axis. Similarly, let me write conservation of momentum along what we say here? Y-axis. Come on, tell me. If I am speaking about along y-axis, conservation of momentum, let me speak like this. So along y-axis, right, is this particle moving along y-axis? No. If no particles are moving along y-axis, then there is no momentum at all. As this particle is moving along x-axis, I took here m1 u1. But here there is no particle which is moving along y-axis. So what is the total momentum before collision here? Along y-axis, that is equal to 0. Right? Okay, here, yes, we have the velocity component along y-axis. So we need to consider now, right? So what is the momentum along y-axis of this particle? So what is that now here? m1. Right? Velocity along y-axis. So do remember, This is V1 cos theta 1. Then this will be along this. What shall I write? V1 sin theta 1. Right? Rectangular components. So this, if it is V2 cos theta 2, this will be V2 sin theta 2, and it is in the opposite direction. Right? Okay, let me write about this. Okay, first write what is the momentum. M1 V1 sin theta 1. V1 sin theta 1. Right? Now, what is the momentum of this? That is M2. M2, what do you get now here? V2 sin theta 2. Right? But these are in opposite direction. Because of that, let me take it as minus. Right? So this is equation number, what shall I write it again? 2. Right? Okay. Now, as this collision is elastic in nature, right? Not only the momentum, even kinetic energy is conserved, right? Okay, let me write. Kinetic energy is also, what we say here? Conserved. Let me write. Kinetic energy is also conserved. So what is the meaning of kinetic energy is conserved? Total kinetic energy before collision is equal to total kinetic energy after collision. Right? Okay, first of all, let me write. What is total kinetic energy before collision? The formula for kinetic energy is half mv square. Okay, let me write this. Total kinetic energy, half m1, what do you get? u1 square. Right? It is not having kinetic energy. Half m1 u1 square. That is equal to. What is kinetic energy after collision? What is the velocity? v1 here. Let me write like this. Half, what do you write? m1 v1 square. Kinetic energy of the first particle plus kinetic energy of the second particle. Half, what do you write? m2, what do you write now? v2 square. Okay, let me take this equation number 3. Right? Okay. This is the kinetic energy of the second particle. So this is total kinetic energy after collision here. Right? This is total kinetic energy after collision. This is kinetic energy before collision. I got equation 1, 2 and 3. If you see these 3 equations, we have 4 unknowns here. Theta 1, theta 2, v1 and v2. Right? Okay, do remember, there are 4 unknowns. There are 4 unknowns. Which are those unknowns? v1, v2, theta 1, theta 2. Right? There are 4 unknowns, but how many equations we have? 3 equations we have. That is why these unknowns cannot be determined by using these 3 equations. Do remember, how many unknowns will be there, that many equations you need to solve it. For example, you have 2 unknowns, x, y. Then how many equations you need? 2 equations you need to solve it. With only 1 equation you cannot solve. If there are 3 unknowns, x, y, z, how many equations you need? 3 equations. If there are only two equations, if unknowns are x, y, z, you cannot calculate. It is also similar thing. How many unknowns are there? 4 unknowns are there. But how many equations we have? 3 equations. So this cannot be determined. Right? Okay. Now, there are 4 unknowns which cannot be determined, by 3 equations. Then what to do now? Let us check it out. So there are 4 unknowns which cannot be determined by 3 equations. So the other go is, let me consider one is known here, right? So by any other experiment we can calculate one value, and other 3 can be calculated by these 3 equations, right? So since there are 4 unknowns are there, we cannot calculate. Let me make one known, means by any other method we will be calculating one quantity, right? Okay. Now let us write like this. Let us suppose theta 1 is known. Let me take like, let us suppose theta 1 is known, means I will be making this as known quantity. Then how many unknowns are remaining here? 3. How many equations are there? 3. Yes, we can solve now, right? Okay. How did you calculate this theta 1? By any other method now here, right? Okay. For, let us suppose theta 1 is known, and let me make much more simpler. m1 is equal to m2 is equal to m. Let me make both the particles are having same mass. Right? Okay. Let me take this condition and let me write these 3. Okay. Do remember, I will be considering this condition, right? And I will be rewriting these 3 equations. We got equation 1, 2, 3. by using this condition, I'll be writing 4, 5, 6. Simple, right? Okay. Now let me write with the first. Let me write from equation 1. Okay. Now from equation 1 here, right? From equation 1, let me put this condition there, right? So what is the condition? M1 equal to M2 is equal to M. Means I will be making M1 equal to M2 equal to M. Means in place of M1, let me write M. Here also M. Here also M. M will get cancelled and M will, if you take the common and they will get cancelled. So what is remaining there? Here what is remaining? This side from equation 1, what is remaining? U1, right? That is equal to M1 get cancels. What is remaining? V1 cos of theta 1, right? Then what is remaining there? Plus V2 cos of theta 2, right? As M1 equal to M2 is equal to M, M get cancels. So what is remaining? U1 V1 cos theta 1 plus V2 cos theta 2. But I will be rearranging these terms, okay, in such a way that the physical quantities of first particle is one side and second particle is another side. Okay, let me make this to come this side. So U1 minus V1 cos of theta 1. Shall I write like this? Okay, that is equal to what is remaining here? V2 cos of theta 2. Right? Just I rearranged. So this is equation number 4. Right? What is equation number 4? Equation 4 is equation 1 itself, but applying this condition. Right? Similarly, let me go with the equation number from equation 2. Okay, in equation 2, where is equation 2? Here is there is equation 2, right? Okay, make M1, M2 as M now here, right? If you take M common, right? So if you take M common, M cannot be equal to 0. Then what do you get there, right? So we will be getting like this, 0 equal to, right? M is removed there. What is remaining? V1 sine of theta 1 minus, what do you get there? V2 sine of theta 2. Shall I write like this? Okay, let me make 1 and 2 separately now here, right? Okay, let me bring this to this side. It will become positive now here. So what do you get now here? V1 sine of theta 1 is equal to V2 sine of theta 2. Okay, let me bring this to this side. So it will become positive now, right? So this is equation number 5. So what is equation 5? Equation 5 is equation 2 itself, but applying this condition, right? Okay, next. Let me take equation 3 now here, right? So we have converted equation 1 and 2. Let me go with equation 3. From equation 3, right? Okay. From equation 3, where it is here, right? M1, M will get cancelled, right? Even half will also get cancelled. So what is remaining here? U1 square, that is equal to, what do you get here? Here, V1 square, right? What do you get here? Plus V2 square, right? So half M will get cancelled. Now let me rearrange. U1 square minus V1 square is equal to V2 square, right? This is equation number 6. That is how I got now, right? Equation 3 is converted into equation 6 by using this condition, right? Simple. See, I got equation 1, 2 and 3, right? By using this condition, I also got equation 4, 5 and 6. Right. What is the aim of this derivation? Here we are calculating what are the final velocities of the particles after collision. Right. I need to find V1 and I need to find V2. Okay. If you see equation 4 and 5, we have V1 and V2s in here. Right. So what I will be doing? I'll be squaring and adding equations 4 and 5. Okay. Equation 4 and 5. I will be squaring it first, then I will be adding, right? Okay, first of all, let me square equation number 4. If I square this term, what is this? A minus B. What is A minus B whole square? A square plus B square minus 2AB, right? Let me write this. Let me square first. That is U1. Shall I write like this? U1 square plus, what do you get now here? V1 square cos square theta 1, right? I have squared this term minus, what do you get? 2 U1 V1, what do you get now here? Cos theta 1. A square plus B square minus 2AB. Okay. Now I will be squaring this and adding. What is this? V1 square sin square theta 1. Right? Shall I add now here? Squared. Okay. This term I squared this term and add these two. So if I square, what do you get? V1 square sine square, what do you get now here? Theta 1, right? Just I squared and added LHS side. Now the same thing I will be doing on RHS side now here, right? Okay, that is equal to, what do you get? Okay, square this term, V2 square cos square theta 2 plus here also V2 square sine square theta 2. Shall I take like this? Right? Here we know we have sine square theta plus cos square theta, right? You know, identity sine square theta plus cos square theta is 1. Let me make like that now here, right? Let me write about this. U1 square plus V1 square. Here also V1 is there, here also V1 is there. In the bracket, what do you get? Cos square theta 1 plus sine square theta 1. Let me write. Let me take V1 square common now here. What is remaining there? Minus 2 U1 V1 cos theta 1. Right? Okay. That is equal to. What is common here? That is V2 square is common. Right? What is remaining in the brackets? Cos square theta 2 plus sine square theta 2. It is nothing but identity. Now let me simplify. So let me simplify and calculate final velocities of the particles. Okay. Now what do you get after simplification? U1 square plus V1 square, because identity is 1 here, right? So minus 2, what do you get? U1 V1 cos theta 1. Cos theta 1. Okay. That is equal to, what do you get here? V2 square, right? So identity I have used, right? Now let me write like this: U1 square plus V1 square minus 2 U1 V1 cos theta 1, that is equal to, shall I write like this? V2 square we have from equation number 6. What is V2 square equal to? U1 square minus V1 square. How did you write this? I have written this by using equation number 6. From equation number 6 we have V2 square equal to U1 square minus V1 square. Now let us check it out. This will get cancelled, right? So what do you get now here, right? So let me calculate now here, right? Let me bring this to this side. What do you get? V1 square plus V1 square, right? Then that is equal to, let me bring this to that side now here, 2 U1 V1 cos theta 1. Shall I write like this, right? So this, what do you get now here? This will be 2 V1 square 2 U1 V1 cos theta 1. Okay, I will be getting what is the value of what we say here? V1 here, right? Now let me consider this will get cancelled, right? 2 will get cancelled. So what do we get now here, right? So we will be getting with V1 square is equal to U1 V1 cos theta 1, right? Here, if I remove V1 also, what we will be getting here, right? So 1 V1 will get cancelled. So what do you get? V1 equal to U1, what do you get now here? Cos theta 1. This is how I calculated. Right? So do remember, just I reshuffled, right? I got this and 2 get cancelled. V1 is also we have common. 1 V1 will get cancelled. What is remaining? V1 is equal to U1 cos theta 1. This is final velocity of the first particle, right? So this is the final velocity of the first particle. Now calculate the final velocity of the second particle. How to calculate this? Okay, let me substitute this equation in equation number 6 now here, right? Okay, let me write. Substituting in equation 6. Okay, in that 6th equation, let me substitute and calculate what is V2. Okay, what do I get? Let us check it out, right? Okay. Now, after getting V1, let me move ahead. Okay, in equation number 6, you substitute here. What do you get? U1 square minus, what is V1? What is V1 there here? That is U1 cos theta 1. Shall I write like this? U1 cos theta 1. That 2 square is equal to V2 square. Shall I write like this? Right? Okay. Now, I want, let me write here, what do you get? U1 square minus U1 square cos square theta 1 is equal to U2 square. Right? Okay. If I calculate this, so if I am calculating Now let me remove u1 square common here. What do I get? 1 minus cos square theta 1 is equal to v2 square. But you know what is 1 minus cos square theta? Sin square theta. So what do you get? u1 square sin square theta 1 is equal to what? v2 square. So what do I want now here? v2 I want. Okay. This is also all terms are square. So shall I write this? v2 is equal to u1 sin theta 1. Right? So let me take square root here. So v2 is equal to u1 sin theta 1. This is the final velocity of the first particle and this is the final velocity of the second particle. Right? This is how we calculated final velocities of the particles after elastic collision in laboratory frame of reference. Next, we will be solving the same thing but considering center of mass frame of reference. Now let us solve the same elastic collision in center of mass frame of reference. We know, we already studied what is center of mass frame of reference. If the origin of frame of reference coincides with the center of mass of the body, then that frame of reference is called as center of mass frame of reference. Right? Velocity of center of mass is 0 in center of mass frame of reference. And it is also called as zero momentum frame of reference, means momentum is also 0 there, right? Okay, let me start with elastic collision considering center of mass frame of reference. Okay, so we'll be starting with velocity of center of mass. We do understand here what is the velocity of center of mass in a laboratory frame, right? What is the velocity of center of mass in center of mass frame here? It is 0. Right, but we will be considering the velocity of center of mass in a laboratory frame here, right? So what do you get now? That is VCM, right? We know that we have studied center of mass, velocity of center of mass. So what do you get now here? M1 U1 plus M2 U2 divided by M1 plus M2. This is the velocity of center of mass, right, with respect to laboratory frame. In laboratory frame, we know that the second particle is at rest. So U2 is at rest. So what do you get now here? That is M1 U1 divided by M1 plus M2. This is the velocity of center of mass in a laboratory frame, right? Okay. So here M2 is 0. So we will be getting it M1 U1 divided by M1 plus M2. Now let me consider what are these U1 and U2. U1 and U2 are the velocities of the particles before collision in which frame? Laboratory frame. Okay, so now we are discussing about center of mass frame. So let me change the terms now here. Right? Let me write, let u1 dash and u2 dash, let u1 dash and u2 dash be initial velocities before collision, right? What is the meaning of initial velocity? Before collision. Okay, let u1 dash and u2 dash be initial velocities before collision, and let me write both now here, then I will be going with center of mass frame here, right? And v1 dash and v2 dash be final velocities after collision, of the particles in the center of mass frame of reference, right? Okay, see here, let u1 dash and u2 dash be initial velocities of the particles before collision and v1 dash and v2 dash be final velocities after collision of the particles, let me write here, of the particles in which frame? Center of mass frame, in center of mass frame. Do you understand? Here I am speaking center of mass frame. That is why I changed the terminologies. U1 dash and U2 dash. Because U1, U2, let me call it as initial velocities in laboratory frame. U1 dash and U2 dash be the initial velocities in center of mass frame. The same thing, V1 dash and V2 dash be the final velocities after collision, that too in the center of mass frame. Right? Okay. Now, we know that center of mass frame is also called as zero momentum frame. Now let us consider center of mass here. This is, let me call it as center of mass, and there is a particle mass m1 which is moving with velocity. What is the velocity? u1 dash, right? Velocity of the particle in center of mass frame. I am speaking with center of mass now, right? Okay, there is another particle whose mass is m2 and it is moving with u2 dash, right? u2 dash with the initial velocity before collision, that too in the center of mass frame. So this is before collision, right? So this is the case before collision, right? So this is the case before collision, right? And let me consider the case after collision. What happens now here, right? This is, let me call this is again the center of mass, right? So this is let me call this x-axis, and the particles move in such a way that, let me take like this, and this is center of mass, right? This is a particle of mass m1 which moves with velocity v1 dash. Yes, v1 dash there, right? Here let me take the particle m2 which moves with velocity v2 dash. So this is the case after collision, right? After collision in the center of mass frame, and we know that in the center of mass frame the momentum of center of mass always remains constant, right? So momentum of center of mass frame is 0, right? So when I speak about the zero momentum frame of reference, right? So do remember, in center of mass frame of reference the momentum will be always equal to 0. That is the reason why center of mass frame is also called zero momentum frame here, right? Okay, now so in order to make zero momentum, the momentum of all two the particles must cancel each other. So let me take the momentum of first particle, that is m1 u1 dash must be equal to minus m2 u2 dash. Then only the total momentum of the system will remain 0 now here, right? So it will become 0 when they will be equal and opposite. That is why this frame is also called as zero momentum frame, right? Okay, from this let me calculate what is u1 dash. What is u1 dash? Minus m2 divided by m1 u2 dash, right? Okay, the same thing here also. Let me consider here after collision. After collision also it should remain the same. m1 v1 dash equal to minus m2 v2 dash, right? Momentum must become 0. When will be the total momentum of the center of mass will become 0? If the momentums are equal and opposite, right? So these are equal and opposite. So we will be getting with v1 dash is equal to m2 v2 dash divided by what we said here, m1, right? Okay, now let me consider about the kinetic energy. For elastic collision, kinetic energy is conserved. Means I can use law of conservation of kinetic energy in this case. Okay, what does it say? Total kinetic energy before collision is equal to total kinetic energy after collision. Okay, what is total kinetic energy before collision? We have there, let us write half m1, what do you get now here? u1 dash square plus half, what do you get now here? m2 u2, right? u2 dash square, that is equal to kinetic energy after collision m1 v1 dash square plus half m2, what do you get now here? v2 dash square. Shall I write like this? Right, total momentum before collision is equal to total momentum after collision. But from here we have the values of u1 dash and u2 dash. Let me substitute here. Okay, what do you get? Half m1. Okay, u1 dash square. So let me make square of this. So it will become positive here. What do you get? m2 square divided by m1 square. What do you get? u2 dash square. Shall I write like this? u2 dash square. Just substitute it. Okay, what do I get here? Plus half m2 u2 dash square. That is equal to half m1. What is v1 dash square? We have there square, that term. It will become positive here. m2 square v2 dash square divided by m1 square. Shall I write like this? Squaring that term. Okay. Plus, what do you get? Half m2 v2 dash square. Right? Shall I take like this? So what do I get? Let's check it out. Half m1 m2 square divided by m1 square u1 dash square plus half m2 u2 dash square is equal to half m1 m2 square v2 dash square divided by m1 square. I got this, right? Here, what do you get? Plus half m2 v2 dash square. Just to observe here, m1 m2 square divided by m1 square. Here also we have the same thing, half we have m2 here. One thing I will be doing, I will be taking u1 dash square common here. What do I get? Half m1 m2 square divided by m1 square, right? What is remaining here? Plus half m2, u1 dash I have removed it, right? Okay, let me remove here v2 dash square, right? What do I get here? Half m1 m2 square divided by m1 square plus half, what do you get now? Half m2. Just check it out. The terms in the bracket are same. Means these two, we can get what we say here, cancel each other, right? As those two terms cancel each other, what do we get? Let us check it out. So we will be getting like this: u1 dash square is equal to what we say here, u1 dash square. Sorry, it is not u1, ma'am. It is u2 here also and here also. This is what now here, u2 is common. Sorry, u2 is common. u2 dash square, right? So u2 dash square is equal to v2 dash square. What is the meaning of this? That is u2 dash is equal to v2 dash. Means the velocity after collision of the second particle will be equal to the velocity before collision. Means velocity will not change at all. The magnitude of velocity will not change, right? Similarly, if I calculate for u1 dash, that will be equal to u2 dash here, right? Sorry, u1 dash is equal to v1 dash. Means the velocity of the particle before collision is equal to velocity of the same particle after collision. Means there will be no change in magnitude. There will be no change in magnitude. There will be no change in magnitude in the center of mass frame. There will be no change in magnitude of velocity in center of mass frame. If I take in the center of mass frame, magnitude of velocity do not change. There is no change in magnitude of velocity in center of mass frame. That means only the direction will change, right? Okay. That is, there is change only in what we say here, direction. Do remember, right? There will be no change in magnitude of velocity in center of mass frame. That is, what is the meaning of that? That is, there is change only in direction, right? So direction is changed, but the magnitude remains the same, right? This is what we discussed about elastic collision in center of mass frame, right? In center of mass frame, we concluded that there is no change in magnitude of the velocities, but there is change in direction, right? So this is how we concluded elastic collision in center of mass frame. So we discussed elastic collision in both one laboratory frame and another one is center of mass frame, and this is all about elastic collision. Thank you.